Hello my friends and business partners from around the world, welcome to my channel. My name is Rafael, I'm an electrical engineer, book writer, business English coach, professional translator and bilingual teacher of mathematics and physics here in Brazil. And in this video, you're gonna see an example of English media instruction related to electrical engineering. We're going to solve an example of symmetrical components applied to three-phase electric power systems. To see the exercise, go to the description of the video. Let me read the problem. One conductor of a three-phase line is open. The current flowing to the delta connected load through line A is 10 amperes. With the current in line A as a reference, and assuming that line C is open, find the symmetrical components of the line current. So the problem wants us to calculate the symmetrical components of the line current. To solve this exercise, we are going to use Fortescue theorem. Do you remember? Have you ever seen the Fortescue theorem? Let's use it. And we are going to decompose these three currents in three sets of currents in positive sequence, negative sequence, and zero sequence. Okay, so what is the difference between them? Let's review the theory before we go to the problem. Positive sequence. What is the positive sequence? Positive sequence is the sequence A, B, C. Okay? A goes first, after A comes B, after B comes C. And they are like this. They are displaced 120 degrees from each other. And the negative sequence, is A, C, B. Now, A comes first and C comes after A. Okay? So it's A, here A, B, C, and here is A, C, and B. Okay? And they all rotate in the same direction, displaced by 120 degrees. And what is the zero sequence? The zero sequence is ABC, but they don't come one after the other like this or like this. They have the same angle. A, B, and C. A, B, and C, they rotate together. A is not in front of B and B is not in front of C. They have the same magnitude and they rotate together in the same angle. Okay, so we are going to use this to solve this exercise here. This is Fortescue theorem. Okay, I'm going to erase it here and let's continue understanding the problem. Fortescue theorem says that we can decompose the line currents using the symmetrical components. So line A, current in line A is going to be IA of zero sequence plus IA of positive sequence plus IA of negative sequence. We're going to do the same for line B. The current in line B is IB is going to be equal to IB of zero sequence plus IB of positive sequence plus be of negative sequence. And in line C, the current in line C is going to be IC of zero sequence plus IC of positive sequence plus IC of negative sequence. Okay? Do you guys know the A operator? A operator is one phase 120 degrees, and we are going to use the A operator, one phase 120 degrees, to write IB0, IB1, and IB2, IC0, IC1, and IC2 in terms of IA, IA0, IA1, and IA2. How do we do that? Let's see how we do that. Instead of writing this here, we write IA0. But why? Because IB0 is equal in magnitude and angle to IA0. So we write IA0 here and the same here, IA0. And how about IB positive, IB1? We simply write A squared IA1. And the negative sequence, we write IA2. Okay? Do you guys understand it? We're going to do the same for IC. And we get plus AI. A1 plus A squared IA2. Okay? Using this, we have everything at hand to calculate the symmetrical components of these currents. So, let's do it. We're going to write it in a matrix equation like this. Continue watching and you are going to know everything about symmetrical components. Let's see, instead of writing the way it was, we can simply put it in this way here. Okay? Have you guys already seen it? Have your college teachers already taught you this? So let's see. We have this here. Okay? A squared A squared, and then we multiply IA0, IA1, IA2. I bet you guys have already seen this in college. If not, I am introducing you to symmetrical components. It is easy, it is not hard. So, we want this, okay? This is what we want. We want the symmetrical components of current A. But we don't have them. So what we need to do is to invert this matrix here. And we are going to use the values that we have. Okay, the exercise gave us these values. We are going to invert this matrix. And we are going to find what we want. What the problem wanted us to calculate. So we simply invert this, the inverse matrix of this matrix in the middle is going to be just as follows. Okay, let's see what we get. So what we want is IA0, IA1, IA2, okay, and we multiply it by a third because it is the inverse matrix of that matrix that we found first, and then we arrive at this matrix here. And we multiply the values that the problem gave us, okay? The problem gave us this. We found this, okay? Using that operator that I told you about, the A operator. The A operator is this. We multiply it by it, and we find the symmetrical components. Okay? Are you finding it easy? Is it easy for you? If it is not, I am going to slow down and I'm going to calculate it very slowly. So let's go. Now what we need to do is to simply use these values here, and we are going to find the symmetrical components. Okay, all right. Now the first symmetrical component that I want to find is IA0. IA0 is then going to be IA0 is going to be equal to a third of IA plus IB plus IC. Okay? We simply put it here and it here. Okay? And then we find that it is 1/3 of 10 phase 0 degrees plus 10 phase 180 degrees. And then we find that IA0 is equal to 0 amperes. Okay? Very easy, isn't it? Okay? If you have an HP calculator, you can simply plug it in, but if you don't, you are going to need to use your knowledge of complex numbers to calculate this. Okay, I'm going to let you use your calculator, and I simply found the value. All right. You can check it later. Use your calculator, please. Now, what we need to do is to find the other symmetrical component, which is IA1. IA1 is then going to be a third of IA plus A. IB plus A squared IC. Sorry, here it is IC. Okay, do you guys agree with me? So let's go. Then it is going to be equal to a third of 10 phase 0 degrees plus 10 phase 300 degrees. And then if you use your calculator, I highly invite you to check this number, which is 5.78 phase negative 30 degrees amperes. Okay, do you guys agree with me? Please check it for me. All right, now that we've found this number, what we need to do is to find the last symmetrical component of current A of line A. The second symmetrical component is then going to be equal to a third. This is the negative sequence of component of line A, which is going to be equal to 10 phase 0 degrees plus 10 phase 60 degrees. Okay, use your calculator, please. And then let's check the value that it is equal to 5.78 phase 30 degrees amperes. Okay, now we have everything. We have everything that we needed. We have everything that we needed. We don't need to calculate much more. We can simply use what we already found. We already found that IA0, IA1, and IA2, they are equal to 5.78. The first is in the phase negative 30 degrees, the second in the phase 30 degrees amperes. Now, to find IB, we simply use the A operator, one phase 100 degrees. We multiply, okay, we multiply, and we find that IB IB0, IB1, and IB2 are equal to 0, 5.78, 5.78, phase, 150 degrees positive, 150 degrees negative here, 100 positive 50 degrees positive there. Okay? Are you guys understanding? Okay, now the last thing that we need to calculate is phase C. So phase C will be equal to IC0, IC1, IC2, okay? They are going to be equal to 0, 5.78, 5.78, and then we need to find the phase. We need to find the phase. Here is phase positive 90 degrees, and here the phase is negative 90 degrees. Amperes, and then we found everything that the exercise demanded us to calculate. So guys, this is the video that I wanted to make. I hope you guys enjoyed and understood everything. If you want to contact me, please leave a message and I'm gonna respond. If you want to book a lesson with me, you can simply contact me via WhatsApp, and then we're going to speak about the lesson. My friends, this was the video. Goodbye!